Welcome back to an Introduction to Real Analysis. We now begin Chapter 4, Section 1, the derivative. So what is a derivative? The idea is the following. Suppose you have a function and you look at its graph. Locally, in other words, very nearby a certain point, suppose the graph looks like a straight line. You can talk about what the slope of that line is. Now this slope will tell you the rate at which the function is changing value at or near the particular point you were looking. Now we're leaving out functions that have corners or discontinuities because there would be no straight line slope to talk about there. And we do need to be more precise about all of this. It's also worth pointing out that we're assuming people have heard of derivatives before and done a lot of these concepts in the past. We're going to be thorough about it, but we're going to move fairly quickly. So let's get to a definition. Suppose I is an interval and f is a function whose domain is that interval. Now pick a point C in the interval. If the following limit, the limit as x approaches C, of f of x minus f of c over x minus c, is equal to L, in other words, this interval exists and is a real number, not plus or minus infinity, then we say that f is differentiable at C, L is the derivative of f at C, and f prime of C is equal to L. This apostrophe prime notation is how we're going to be denoting derivatives. Now suppose the function is differentiable at every point in the interval. That previous limit exists at every point in the interval. Then we can simply say that the function f is differentiable on the interval, and we define a new function f prime, which maps the interval to the real numbers, defined through this previous limit. We're going to call that the derivative of f. Now this expression f of x minus f of c over x minus c is called the difference quotient of the function f at the point c. The graphical interpretation of what we're doing is as follows. Suppose at right we have the graph of some sort of function. What is the slope of the line connecting the 2 points x comma f of x and c comma f of c? Well, the difference quotient is exactly the slope of that line, the change in y coordinate f of x minus f of c over change in x coordinate x minus c. So the derivative is therefore a limit of this secant slope as the variable point x comma f of x approaches the fixed point of c comma f of c. The slope is often called the slope of the tangent line at the particular point. This is a term that is technically well defined. It's simply defined this way, but many people view tangent lines through sort of geometric notion. So in example 4.1.2a, there will be an example of why this geometric notion of what you might think of the word tangent meaning is not always completely appropriate. We should make a comment regarding endpoints. We've defined the derivative at c through this limit of the difference quotient wherever you have a point c in an interval I. Now, if the interval is of the form from a to b including the endpoints, there's no reason you cannot pick c to be either a or b, one of the endpoints. We defined limits through cluster points, and a and b are cluster points of this interval, so this limit is totally reasonably defined. If you compare this to most other texts, this isn't exactly how derivatives are taken. In most other texts, you would need to take this limit up above as a two-sided limit rather than defined through cluster points. This is a minor distinction. It does affect how some theorems are stated later on. Just bear in mind, we defined limits at cluster points, and the way we defined it, both a and b are cluster points of the interval, in which case this limit is totally reasonable. If you compare to more standard definitions, our limit as x approaches a would be the same thing as the limit as x approaches a from above, and our limit at b would be the same thing as the limit as x approaches b from below. We just went through the rigmarole of defining through cluster points so that we don't have to adjust our notation in that way. Let's take a look at example 4.1.2a. This is a new example introduced to point out something specific. Earlier we mentioned that the term tangent line is not always exactly what people think it is. Okay, the most formal definition of a tangent line commonly introduced is you look at a line that goes through the point c comma f of c, whose slope m is chosen in such a way so that the line best approximates f of x as x approaches c. Now in that definition, the slope m is f prime of c. That's exactly the single unique value of the slope of this line to get the best approximating line at a certain point. However, There's a common intuitive notion of what a tangent line means, in that it should somehow bounce or deflect off a curve or only touch the curve at a single point. Now, the notion of only touching the curve once is definitely not right. Here's a picture we had up earlier. The orange line certainly appears to be tangent, but it definitely intersects the curve somewhere else. Okay, now that's just a minor distinction. I mean, the line intersects the curve all the way over here. Most people, however, understand what you really meant is that nearby it only touches the curve once. So now let's look at a different function, x squared times the sine of 1 over x, at least for all x not equal to 0. However, if you simply squeeze this down compared to x squared, you'll see that the limit as x approaches 0 is exactly 0. Then, if you compute this difference quotient, you just get x times the sine of 1 over x. Therefore, you can take a limit as x approaches 0 and see that the derivative exists at 0 and is equal to 0. Now here's a graph of that function, x squared times the sine of 1 over x. The tangent line is simply the x-axis, y equals 0, the tangent line at the point 0, 0. However, this line intersects the curve infinitely many times on any interval around 0. Okay, this curve is essentially a sine curve, but it's going up and down faster and faster as you get closer to the origin. So no matter how much you zoom in here, the quote tangent unquote line is going to be intersecting this curve infinitely many times. Okay, this is just to point out that the definition of tangent line is not really a geometric one in the sense of bouncing off a curve or intersecting only once, even though in elementary texts that tends to be a picture that's drawn. The definition of tangent line is line of best approximation at a certain point, and then you'll find that the slope has to be given by the derivative. Okay, so this is just a modification of definition. Just be mindful of it. That tangent line doesn't mean intersects once. It means line through a point on the curve that best approximates at nearby values. So here's example 4.12. Just take f of x equals x squared. We're going to compute the derivative and see that f prime of c is equal to 2c. This is a fairly straightforward computation. For all x that are not equal to c, if we compute the difference quotient, we're going to exploit this difference of two squares factoring in the numerator to cancel out our denominator and simply get x plus c. So the difference quotient is always equal to x plus c. Now we can take a limit of the difference quotient as x approaches c and just get 2c. The next example, suppose a and b are real numbers and let f of x be a line, ax plus b. Then the derivative is exactly equal to a everywhere. Again, we can simply compute a difference quotient, f of x minus f of c, ax plus b minus ac plus b. The b's cancel, you can factor in a and cancel out the x minus c's, and you just get a constant. Now we can simply take a limit as x approaches c of this constant, and we're done. Another example, f of x equals root x. So once again, we need to compute this difference quotient. Okay, we can't just take a limit as x approaches c straight away. We'd be dividing by 0. That will always be the case. But here is f of x minus f of c. We're going to rationalize by multiplying by this conjugate, root x plus root c. The benefit is that turns the numerator into exactly x minus c, which can then cancel out that shared factor down in the denominator. So our difference quotient is simply 1 over root x plus root c. And as long as c is not equal to 0, now we can take a limit as x approaches c and end up with 1 over 2 times the square root of c. Another example, f of x equals absolute value x. This has derivative 1 for positive c, negative 1 for negative c, but does not have a derivative at c equals 0. So for all x that are not equal to c, here is our difference quotient, absolute value x minus absolute value c over x minus c. Now, when c is positive, as x approaches c, x must also be positive. Similarly, if c is negative, as x approaches c, x will have to be negative as well. So, when c is positive and x being very close to c means x is also positive, the absolute value function functionally does nothing. We end up with x minus c over x minus c, and that's just going to be 1. So if we take a limit as x approaches c of that constant 1, you get 1. Similarly, when c is negative, as x approaches c, x must also be negative, meaning the absolute value of x is minus x, and the absolute value of c is minus c, which now turns that minus to a plus. Factoring a minus 1 out of this and canceling, we have the constant minus 1. So taking the limit as x approaches c of this constant minus 1, we obtain our derivative there as well. So the derivative exists and is 1 when c is positive and minus 1 when c is negative. So what happens when c is equal to 0? Now, x is approaching c, meaning it's not equal to c. So we have two cases. As x approaches 0, we have to consider when x is positive and when x is negative. Following exactly the same computations from the previous slide, when x is positive, the difference quotient is simply 1. When x is negative, the difference quotient is simply minus 1. So if you take a limit as x approaches 0, the two one-sided limits are different. There is no limit overall. Let's talk about the relationship between differentiability and continuity. So a famous example of Weierstrass, the same one from Bolzano-Weierstrass, shows that there is a continuous function that is not differentiable anywhere. The construction of this function is beyond our scope, to be honest, but here it is. It is constructed through a series, a to the n times the cosine of b to the n pi x, where a is between 0 and 1, b is a positive odd integer, and the product ab must be sufficiently large. The rough idea is that since a is less than 1 and you're multiplying by a to the n, and cosine is bounded, the terms in this series are exponentially small, so convergence is not an issue. Also, that is how you end up with continuity. However, b is fairly large, especially compared to a. A times b is sufficiently large. This guarantees that this cosine function has a very, very small period because you have cosine of b to the n, which is going to be quite a large number, times pi x. So you have a series of a bunch of cosine curves of a very small amplitude, but very, very small period. So you're adding together a series of very quickly oscillating tiny waves. And you end up with something that looks sort of like this, picture taken from Wikimedia. And no matter how close you zoom in on any particular point, you see the same bumpiness because of these very, very small amplitude, but very, very small period cosine waves. Okay. On the other hand, the reverse can't be done. If a function has a derivative, it must be continuous. So let's prove that. Suppose you have a function and it is differentiable at a point, then it must be continuous at that point. Okay, the proof is not terribly long. So we have the following limit. F prime of c, which we have assumed exists, is the limit as x approaches c of f of x minus f of c over x minus c. However, the limit as x approaches c of this linear function x minus c, this is a straight line, it's continuous, we can just plug in x equals c, we end up with 0. So we can multiply the two together. 0 times f prime of c is the product of these two limits. Since we know both limits exist, we can combine them into a single limit. And whatever f prime of c is, it has to be non-infinite. That's part of our definition. So 0 times f prime is 0. This overall limit, we can now cancel this denominator out, and we simply get the limit as x approaches c of f of x minus f of c. So we've computed that 0 is equal to the limit as x approaches c of f of x minus f of c. We also know that the limit of a constant is itself, so let's let that constant be f of c and add that limit to both sides. On the left, we add the constant f of c. On the right, we're going to represent it as the limit of the constant. Since both of these limits exist, we can combine them. The f of c's cancel, and here we have it. F is continuous at c. Now, an important property of taking derivatives is linearity. And by linearity, what we mean is an operation that distributes across sums and scalars may factor out. The derivative is the approximation of a function by a straight line, and the slope of a line through 2 points changes linearly when the y-coordinates are changed linearly. That's essentially how the proof is going to proceed. Taking the limit, that's the tricky part, and that's what we'll work out. So here is proposition 4.1.7. Suppose f and g are two differentiable functions on an interval, and let alpha be a fixed real number, a scalar. Then both alpha times f and f plus g are also differentiable on the entire interval, where the derivative of alpha f is simply alpha times the derivative of f, and the derivative of f plus g is the derivative of f plus the derivative of g. Okay, let's get proving. So the proof is going to be a straightforward application of this previous corollary, corollary 3.1.12, which had to do with distributing limits in a linear fashion across functions. So first, let's look at the difference quotient for alpha f. Alpha times f just means alpha times f. So we have alpha times f of x minus alpha times f of c. The scalar alpha now factors out of that entire thing. And from this previous corollary, since I can take this limit, our assumption is that f is differentiable, this scalar factors out of the limit, giving us the first result of proposition 4.1.7. Now let's take a look at the second half. So we'll take the difference quotient of the function f plus g. So this gives us f of x plus g of x, and then f of c plus g of c, and we distribute the minus sign. Collecting the two f terms and the two g terms, I can now split this up into two separate limits because our hypothesis is that both of these limits exist. So if we take a limit as x approaches c, we obtain the second half of proposition 4.1.7. Now, despite the fact that limits distribute across products under general conditions, this follows from corollary 3.1.12, it's not true that the derivative of f times g is f prime times g prime. Instead, we're going to derive the product rule, aka the Leibniz rule. We'll also establish how differentiation interacts with composition of functions through the chain rule, perhaps the single most useful derivative law, although of course that's difficult to quantify in any reasonable way, but the chain rule is a very big deal. We'll get to that shortly. The other common general derivative rule has to do with inverse functions. That's going to be in a different section. It's coming up soon. So here is proposition 4.1.8, the product or Leibniz rule. Suppose f and g are two differentiable functions on an interval. Then the product function f times g is differentiable, where the derivative of f times g is given by f prime times g plus f times g prime. Let's visualize this product rule before we actually prove it. So the proof is actually left as an exercise, but here is a picture that really establishes what's going on. So here we have f of x times g of x minus f of c times g of c is equal to, now algebraically, this is just a matter of distributing everything out and seeing what happens. Here's your f of x g of x, here's your minus f of c g of c, and your other two terms are f of x times minus g of c, f of x times positive g of c. So algebraically, there's not much going on here, but what is happening? Think of x, g of x and f of x being slightly larger than g of c and f of c, just so the picture makes sense. Then this large rectangle is of area f of x times g of x, whereas this smaller area is f of c times g of c. Taking the difference leaves this horizontal stripe and this little vertical one, marking off that this gap is g of x minus g of c, and this overall width is f of x. Similarly, this height here is f of x minus f of c, and this height here is exactly g of c, gives us this exact formulation. It's merely a visualization of what is algebraically obvious. So let's move on to the quotient rule, 4.1.9, since the product rule, again, is left as an exercise. Suppose f and g are two differentiable functions on an interval. Also, let's assume that the function g is never 0. Then the quotient f over g is differentiable everywhere in the interval with the following formula. F over g prime is given by f prime times g minus f times g prime all over g squared. A handy little mnemonic that someone told me a few years ago is that the quotient rule can be remembered as, if f you consider high and g low, you have low d high minus high d low over low squared. Low d high minus high d low over low squared. At least for me, it kind of stuck and I didn't have to look it up anymore. And yes, I was looking up the quotient rule well past my PhD, just because it's the sort of thing that you never bother to commit to memory. Until you start teaching calculus, at least, and then it'll stick. So the proof of the quotient rule, much like the product rule, it's left as an exercise. A direct proof is formally doable, but honestly, no one proves it directly through the difference quotient of that quotient of functions. The more common proof is to separately compute the derivative of the function f of x equals 1 over x. You can do that directly. Then you throw the chain rule and the product rule, observing that f of x over g of x is f of x times 1 over g of x. So we can derive the derivative of this quotient by looking at this product of f of x times 1 over g, then think of 1 over g as a composition of the function 1 over x with g of x. That's the more straightforward way to do it once you are told that that is a good way to go about it. Okay. The chain rule, however, we are going to prove. We just glazed over the product and quotient rules. Their proofs are left as exercises. The chain rule, however, we're getting to. So here we have it, prop 4.1.10, the chain rule. Suppose I1 and I2 are two intervals, not necessarily different, not necessarily disjoint, just two intervals. I1 is the domain of G, and its codomain is I2. I2 is the domain of F, and its codomain is whatever in the real numbers. Then we also assume that G has a derivative at C, and that F has a derivative at G of C. Then we can compose f of g, and its derivative at c is given by f prime of g of c times g prime of c. Now earlier we mentioned that the derivative of the product f times g is not f prime times g prime. That's the naive product rule, so to speak. The chain rule is where that actually happens. Here we have f prime at some point times g prime at another. So you do end up with this product of derivatives, but it's not when you take the derivative of a product, it's when you take the derivative of a composition. Also, you end up with the only thing that could possibly make sense on the right-hand side. The only place we assumed g has a derivative is at c. The only place we assumed f has a derivative is at g of c. Why were those our assumptions? Because the composition will feed c into g and then feed g of c into f. This theorem could not have been stated differently, in other words. That said, so let's get to proving the chain rule. For convenience, we're going to let d represent the point g of c. This is simply a notational issue so that we're not writing so many parentheses everywhere. We're going to define two functions u and v as follows. Essentially, u of y is the slope of a secant line connecting the point d f of d to y f of y. Now that can't be done when y equals d. However, d, aka g of c, is exactly the point where we assumed f has a derivative. Similarly, v is the slope of the secant line connecting c g of c to x g of x. We can't do that when x is equal to c, but that's exactly where we assumed this derivative exists. Now, our differentiability assumptions tell us that f and g are continuous at d and c respectively. Remember, wherever a derivative exists, the function must be continuous. It is worth pointing out we did not assume f and g are differentiable or even continuous anywhere else on their domains, just at c and d for g and f respectively. However, since f and g are continuous at these points, so are u and v. The limit as y approaches d of u is given by the limit as y approaches d of this difference quotient, which is equal to the value of the derivative, which is the value of u of d. Similarly, the limit as x approaches c of v of x is the limit of this difference quotient, which is by definition this derivative, which is also equal to v of c. So u is continuous at d, v is continuous at c. So here were our definitions of those functions u and v. Now for any points in I1 and I2, we get the following equalities. Let's take a look at this one on the left. If y is not equal to d, you can divide this over and you simply get the definition of u, at least when y is not equal to d. However, if y does equal d, here you get 0, but if y equals d, you get 0 on the left as well. Similarly, if x is not equal to c, divide that over, get the definition of v. If x does equal c, you get 0 equals 0. So regardless, we have these two equations. All right, so now we have these. we're going to compute the numerator of the difference quotient for the composition here. F of g of x minus f of g of c. F of g of x minus f of g of c. Now to end up here, just use y equals g of x and remember that d is equal to g of c. So f of g of x minus f of g of c equals u of g of x times the quantity g of x minus g of c. That's exactly what we have here. Overall, we have that the numerator of the difference quotient for the composition can be written as u of g of x times, well, g of x minus g of c. Hey, g of x minus g of c is exactly v of x times x minus c. Why would we go through all this? Because with this at our disposal, we can divide out x minus c and end up simply with u of g of x times v of x. Now we can take the limit as x approaches c. On the left, we'll get the derivative of f composed with g. And on the right, we are going to take the limit as x approaches c of this expression right here. So we're going to show that the limit as x approaches c of u of g of x and v of x both exist. So what's the limit as x approaches c of v of x? We already remarked that v is quite specifically continuous at c. So what do we obtain? Just v of c, aka g prime of c. Now let's take the other limit that we needed to compute. Specifically, we need to take the limit as x approaches c of u of g. Here was our definition of the function u. Now remember that u is continuous at d, d is equal to g of c, and g is continuous at c, because g has a derivative at c. So let's recall Prop 3.2.7. The composition of continuous functions is continuous. So representing y equals g of x, this is now the composition of two continuous functions at a point of continuity. So how do we compute the limit as x approaches c of u of g of x? We can simply plug in x equals c, u of g of c, that's u of d. What's u of d? It's exactly f prime of d. What was d? It was g of c. So overall, this limit is exactly f prime of g of c. So to wrap it up, here was our difference quotient for the composition. Taking a limit as x approaches c, we've just shown that this term and this one both have limits as x approaches c. And specifically, they're exactly the two terms we want to get. So we can take the limit as x approaches c of both sides and complete the proof of the chain rule. So what did we do here? It's worth stating, a lot of people who have taken elementary calculus courses and are now doing this proof-based approach, now that we talk about derivatives, they feel, finally we're doing calculus, but we had to build on limits of functions and what is a limit and all sorts of previous materials. So we're really putting together a lot of pieces that we've set up. It's worth mentioning one can define derivatives in different ways. They should be consistent with one another for straightforward functions. This is the typical way that you define derivatives. It's good enough for most purposes. We've also proved major rules for differentiation, and by proved, at least in the case of the product rule, I mean leave as an exercise, but we did prove linearity in the chain rule.